now we're going to invite that program, also known as Ron Evans, to talk, maybe cause some accident, injure some people, who knows, with the power of Go. So, round of applause for Ron.
Thanks, Frances. So welcome, everybody, to Gopherpalooza here in the beautiful city by the bay. What beautiful place. And I just want to take this moment. Let's give up a round of applause to Gray, to Vicky, to Elena, to all the other organizers and staff here at the conference. These things are really a labor of love, and we all really appreciate it. So I am Dead Program. In the real world, some people call me Ron. A couple humans call me Dad, but I am Dead Program on Twitter and GitHub and all the internets. And I run a consultancy called the Hybrid Group. So we do software for hardware companies, and we've done some work for clients like a little company called Intel. And we did a lot of work for a company called Sphero that's known for creating robots used in movies about wars in the stars, and that's all I'm allowed to say about that. Just pretend like that slide didn't have any logos. So we've done a lot of work in the open source world, and particularly in Go. One of our projects is one called GoBot that quite a few people have used for creating robots, drones, and other internet-connected devices. And the newest project that we've been working on is something called GoCV. That's what I'm here to talk about today. So GoCV lets you use OpenCV from the Go programming language. So OpenCV is a framework for computer vision applications that has literally hundreds of algorithms and filters for all of the different capabilities and features that you'll need for building some type of computer vision application. And so GoCV lets you use OpenCV from the Go programming language, our favorite language, of course. So it also lets you use Go with OpenVINO, which is a special hardware-optimized build of OpenCV that also includes some deep neural network inferencing capabilities, but I'm not going to actually show OpenVINO today. So first of all, what is computer vision? So according to Wikipedia, it's any artificial computer software that's designed to mimic or emulate the same kinds of visual processing capabilities as those possessed by a human being. So well, that's neat, but what does that mean? What can we actually do with computer vision? Well, we can do things like detect motion. We can recognize people. We can perform telepresence, which is when you are as if you were somewhere else, like some of the robotic vehicles that are on other planets and asteroids and comets. Autonomous vehicles, whether that's planes, trains, automobiles, or my personal favorite, multicopters. Augmented humans. So when Tim O'Reilly said the purpose of the Internet of Things is to give humans superpowers, and we usually think of, obviously no capes, that's a given. But thank you, at least someone's an Edna fan. But I think about it more like it's giving us abilities to do things. Sometimes it's perhaps to see in spectrums of light or to know there's details we might not otherwise see. For example, when the radiologist is analyzing all of your different reports, being able to recognize features that require further investigation would be a much more useful superpower to most people than flying. So why you should use Go for computer vision? Well, it's for the same reasons you should use Go for everything, of course. Come for the concurrency, stay for the portability, and naturally the performance, starting with Go 1.9 in particular, the performance of the garbage collection inside of Go is really, really impressive, and the benchmarking work, an ongoing optimization that's done by the team, it's really spectacular. And so these are reasons why you want to use Go for everything, and especially computer vision. So how GoCV works, so OpenCV itself is actually written in C++. So in order to use GoCV, we need to have our Go code, which calls C code using CGo, and then our C wrappers then call the C++ wrappers. So that sounds really ugly to some people, but it's actually very similar to the way that Go itself is calling the operating system. So this is just a quick diagram. It shows your Go application doesn't have any need to be aware of what operating system you're running on. It will call the GoCV Go functions, which provide a more idiomatic Go interface, despite the C++ nature of what you're calling the GoCV C wrappers, and then calling OpenCV itself. So it lets you write the same exact Go code and execute it under Linux, under Mac OS, and under Windows. Yes, I said Windows. So I know we're in San Francisco and we're all way too cool to use Windows, but there are actually many, many millions of developers, just like us, out in the world who use Windows as their primary operating system for development and for deploying their applications. So we really need to care about Windows users, even if we are not Windows users ourselves. Anyway, small rant, disengaged. So let's get into some actual code. So we'll start with the hello world of video. So the hello world of video is, can we see this? Oh, okay, perfect. By the way, note to presenters, please always use white background because some of us don't see very well, and that's why we work on computer vision software. I just hope to retain what side I have left from my natural life. All right, so let's get into some code. So package main, the same as any Go program. We're going to import the GoCV package from the gocv.io/x/GoCV, and then we have our function main. So the first thing we're going to do is we're going to call GoCV video capture device, passing it 0. So this is going to open up our webcam 0, which is just going to be the default camera that's built into my notebook computer. Then we're going to call GoCV.newWindow. That's going to open a display window so I can actually see what the camera can see, and that's going to assign this to the window variable. And then we're going to call GoCV.newMat. This is going to create an OpenCV mat, which we'll talk about more in a minute, and it's a place for us to put the image that we're going to capture. Then we're going to call webcam.read. We're going to pass into the pointer to the image because we're actually modifying that image itself. So in order to comply a little more closely with idiomatic Go, we're saying you can expect that this will actually be modified by calling into this function. Then we're going to call window.imShow, passing it that image. So it's going to open the window and show the image. Then we'll call GoCV.waitKey 1 second. That's going to wait for 1 millisecond for us to press a key or something, and then loop again and show the next frame from the webcam. So if the gods are good, is that big enough? Let's make it a little bit bigger. There we go. And there I am with my microphone. Yo. All right, so gratuitous applause, please. I'll take it. I'll take any of it. All right. So let's get into the mat tricks a little. So what is a mat? So in OpenCV, the mat is the fundamental data type, and a matrix in mathematics is typically some type of numbers that are arranged in rows and columns. So that is also the case with a mat in OpenCV, but it can also do a lot more. So we start with an empty mat. So I'm going to explain everything in terms of Legos because that's something I can understand, more or less. So an empty mat is just like an empty base plate. There's nothing on it. It has no actual value, but we can test to see if it's empty or not. So that's our starting place. So if we wanted to represent a grayscale image in terms of a mat, well, it would be a two-dimensional mat. It would have an X and a Y. And then each one of the elements would be a 16-bit integer. That way we can represent the different levels of gray that we need to represent a grayscale image. So it would be a 2D mat of 16-bit integers. So it's important to mention that every element within a mat has to have the same type. So here's a way that we could represent an RGB color image. Mats can also have dimensions and channels. So in this case, we have 2 dimensions. We have an X and a Y of 16-bit integers, because that's how we're going to represent the red, the green, and the blue. But this time we have 3 channels. Each pixel has 3 channels, one for each one of the different color variations. And this is something that you see very commonly when you're working with any RGB colors. We can also have an alpha channel for transparencies. So this is the typical kind of way that we represent a color image in OpenCV. But we can also represent more complex types using a mat. This is a 3D vector. It's a 3-dimensional mat that consists of floating point values of 2 channels. So maybe we want to represent a three-dimensional point cloud of data that we're analyzing from some type of stereoscopic type of or 2D feature analysis. So this is a way that we could represent more complex data in OpenCV and consequently in GoCV. All right, so let's get real. Let's show 4 real-world applications using GoCV. And so these are really very common. If you do a search on the Googleverse for OpenCV, how do I, and then once you get past install, which is like the first 3 results, different flavors of that, then you get into some of, these are some of the applications. So the first one is, let's do face tracking. But you know what? Face tracking isn't cool anymore, is it? I mean, really? The cool thing now is face blurring. Now that is cool. Yes, thank you, civil libertarians. So first we're going to have to track the face in order to blur it. It's kind of like we had to destroy the village to save it, maybe. I don't know. It depends if the data leaves the device or not. So the way that we're going to do that in traditional computer vision is we're going to use something called a Cascade Classifier. So a Cascade Classifier uses a field of mathematics known as Haar wavelets in order to perform a kind of signal analysis, not unlike a Fourier transform, where we can take a signal and we can break it apart and analyze it in terms of these 4 different classifications. So 2 researchers, Viola and Jones, discovered a number of years ago that you could apply this to face tracking. So by taking these Haar features, you know, your eyes are a little darker than your cheeks. So if we take this feature where it's a little darker versus a little lighter, and a picture of my son Manolo, and we superimpose, we could see, okay, so there is an eye feature on that image. We could do the same thing to the nose. The nose sticks out a little bit from the cheek, so it's a little bit brighter relative to the cheeks. So in this case, same idea, we're applying this Haar feature. So, or we can just use the GoCV.Cascade Classifier, which is the feature that's built into GoCV to show OpenCV's ability to use that. So we'll take a quick look at some code. We won't go over every line. First, we're going to import some standard packages from the Go standard library, Funct, Image, OS, and StirConv. We're going to import GoCV, and then we're going to have pretty much the same pattern, application pattern as what we had before. First, we're going to just parse some arguments that come in so we can pass in the camera to use and the training data file to use for the facial recognition. We're going to open our webcam, again using GoCV.video capture device. This time we're going to actually look at the error value coming back, and if something went wrong, we'll just close, or return rather. Otherwise, we'll defer webcam.close so that we can close up the memory allocated by the C portion of this application. We just ignore that in our hello world of video, because when the program terminates, it'll just free up whatever memory was allocated by the process. So then we'll open our display window, same as the previous hello world, using GoCV.new window. We'll prepare our single image matrix for storing our data. And then we'll load our Cascade Classifier using GoCV.new Cascade Classifier. And we'll load that into this classifier variable. And then we'll load the classifier with the data from an XML file that's got the Haar Cascade information for facial recognition data. Then we start forever, once again reading the camera, same exact as before. This time we check to see if the image is empty, and if so, we just loop again. Otherwise, we'll call classifier.detect multiscale. That will perform multiple attempts to cascade and look through that image for all of the different faces that we can find in the image. And when it finds them, it will return them as a slice of image.recs. That way we're dealing with standard Go, standard library types. So then for each one of those faces that we've detected, we will then grab the region of that face, because we only want to blur the face, right? This is the Microsoft video conferencing software that I forgot the name of right now. Some Microsoft people know, but it blurs everything behind you. I'm going to do that for my next demo. This only blurs your face. So it lets everyone know where you are, but not who. So perfect for many people like myself. So we're going to grab the region, only the face, and then we're going to call GoCV.Gaussian blur. So we're going to blur just the face part, and then we'll close that mat that we opened with only the region. Then we'll display the image. We'll wait for 1 millisecond. If you press any key, then we'll exit the software. All right. So if the demo gods once again favor me, as they sometimes do, sometimes not, I'm used to performing with a mic, but usually I have a guitar at the same time. So, all right. So we're going to use camera 1 this time. Oh, and can I get the lights turned on? All right. So there's me, and you see my face is blurred. Actually, we could open this a little bigger. That'd be easier. But let's take a look at all of you. What? This is how you know it's real. You got to look at the camera for it to recognize that you weren't here. There's whole sections of this place that weren't here. Oh, there we go. All right, so one thing about Cascade classifiers is that they're only so permissive. You'll notice if I turn my head very far, it's no longer able to blur because it's no longer able to recognize that actually oh, maybe that was the problem the whole time. It's not able to recognize me if I turn my head too far. So, I mean, of course, very nasty people looking at this video will recognize me because I turn my head away from the surveillance camera just at the right angle. So it's not optimal in all cases. It has its limitations, but this is an example of using traditional computer vision for doing facial blurring. All right, and so that's that one. Thank you, thank you. All right, let's do, next let's do motion detection and tracking. So for this, we're going to do something called background subtraction. So background subtraction, we're going to use something that's called a mixture of Gaussian. So quick refresher, Gaussian distribution is a normalized distribution, the classical bell curve. So we can analyze the different red, green, and blue by performing the same type of Gaussian distribution analysis. It's known as a mixture of Gaussian. And if we take this mixture of Gaussian and we do it for each one of the pixels, we can do what's known as a running mixture of Gaussian. So this is how we can determine the background, which is not changing, versus the foreground, which is changing because of just performing this type of analysis, or in terms of the signal processing of the visual data that's coming back in that image mat. Or we can just call GoCV's .background subtractor mog2. So that's the background subtractor mixture of Gaussian version 2. There was an earlier one, but mog2 is much more efficient in terms of computational resources. So a quick look. Same idea, import some of the standard packages and GoCV. Same idea of a main. It's the same application pattern. We parse some command line parameters. We open the camera, same as before. We open a window to put our results in, same as before. This time we're going to create a few different image mats. We're going to have the image mat that we're going to capture into. We're going to have the delta, which is basically only the foreground, right? It's the things that are changing versus the things that are unchanging. We're going to have image threshold because we're going to do a threshold filter so we can get rid of some of that noise that will inevitably in this resulting image. And so that's where we're going to place that. And then we'll have mog2, which is where we're going to place the GoCV.new background subtractor mog2 struct, which we'll call into OpenCV and perform our calculations. Same pattern as before, forever. We read the webcam into the image. If it's empty, we loop. Otherwise, we apply the mog2 algorithm to the image, putting the result into image delta. Then we perform our threshold calculation, which is going to clean up the image, getting rid of any of the pixels that are either not strong enough or too strong, so it gets rid of the extremes. And we're going to place that into the image thresh mat. Then we're going to do a little bit extra cleanup by calling the dilate. Dilate basically swells up to fill in all of the little gaps that are missing in the edges. And then once we've done that, we're going to call GoCV.find contours. That calls into OpenCV in order to do contour finding based on the external. It's going to start on the outside and work its way in versus on the inside and work its way out. For each one of those contours we find, we're going to take the contour area. If it's too small, then we're just going to loop. Otherwise, we're going to draw an outline of whatever contours of the thing that it found, and we're going to draw a rectangle around that whole thing so you can see within the contours, here's the area that's affected. And we'll do that for each one of the contours located. We'll put some text onto the image saying whether or not we found something, our status, and then we'll loop again after showing the variable or showing the image in the window. All right. So now if we copy and paste our code, because that's how real programmers do it. Yes, please. Yeah, sorry, I forgot my AV cues. All right, so now this time let's get rid of this camera, because that's my wide-angle lens. And then let's plug in my creative. I found that the more common the camera, the better the Linux drivers. Like the cheapest possible camera usually works perfectly, and the really expensive one, almost never. Am I the only one who figured that out? All right. So we'll run that. And there I am. I'm going to have to get out of the field of vision a little bit. The stage is moving a lot. Can you feel it? But you can see where it's finding the different areas, it's finding the different contours, and it's still within the range of motion. But you can see that it's able to determine the background versus the foreground, and it's creating this really cool cyberdelic effect, which, yes, you're welcome. No hangover either, it's great. All right, so that's motion detection using GoCV. All right, let's show our third application now, which is web video streaming. Everybody always wants to do web video streaming. Like this is like the most common thing that with a camera is how do I do some type of image processing and then put it on the internet. A good example of this might be a homebrew telepresence robot or something like that. You want to be able to drive it around your house and see what your cat's doing. So how do you get that video from the camera into a web browser? Well, we're going to use something called MJPEG for motion JPEG. And it's pretty much exactly what it sounds like. It's just JPEG frames one after another. It's a standard that's been built into every web browser for a long time. There's no plugins. There's no separate encoder or decoders, rather, that are required. So we can use MJPEG. So this is a slightly more robust design pattern for the application. We're going to do the same thing as we did before. We're going to import some standard package libraries. We're also going to importantly import net/HTTP, because that's what we're going to use for our web server, is just the standard libraries web server. So then we'll import the hybrid group /MJPEG package. This is originally from a person who disappeared a couple of years ago and hasn't done any commits. So we're similar to that example that was used earlier of during the packaging talk, where we're like it's now on us just to maintain this. So anybody who finds that part interesting in particular, please take a look. And then GoCV. So now we're going to declare a few different variables here. That way we can use them within the different functions that we're going to declare. Right? We have our device ID, which camera, an error of which could be returned, a pointer to the GoCV.video capture of webcam, because that way we can use the webcam from more than one Go routine, and then a pointer to our MJPEG.stream. That's how we're going to actually put the streaming data into our HTTP server. So same as before, a main function where we parse some command line parameters. We'll open our webcam using GoCV.video capture device. This time, though, we'll call MJPEG.newStream, which is going to allocate a new stream struct, and that's what we're going to use to serve up the MJPEG frames. And then we'll start a Go routine, Go capture. That's what's actually going to capture each one of the frames from our webcam. Then we'll HTTP.handle / is the route. That means, and we're going to serve upstream on that root of the web server. So the root of the web server is going to be our streaming MJPEG video. And then, as you've seen many times, we're going to call log.fatal HTTP.listen and serve. This is just starting up your normal, everyday Go standard library web server like you've seen a million times. So then our Go routine, our capture Go routine, we're going to allocate a new mat to capture the next frame into. This time you can see why it is important for us to defer image.close when we get out of here. And then forever, same as before, we read the image into the mat, loop if it's empty. Otherwise, we call GoCV.ImEncode, which is an OpenCV to encode the current image mat into whatever format, in this case, a JPEG, and just put it into a buffer of memory. So it's just a raw buffer of memory with a JPEG image. And then we call stream.update JPEG buff. So we say, serve up this JPEG as the current stream for as many clients as are currently calling upon our web server. So it's like all Go software, very, very scalable. So let's run it. Go back to my copy and paste of all my code, because I'm a copy and paste kind of guy. Some people are like, this code the hard way. I'm like, oh, no, code the easiest way. It's still going to be hard as hell. All right, so we're going to call with camera 1, and then we're going to pass in 0.0.0.0:8080, so it'll serve up on localhost on port 8080. So now it's point our browser to this, which help if I could see where to type anything. Localhost 8080. Hey, and check out that guy. He's on the web. I'm internet famous. Hi, everybody. Hi, Mom. So, I mean, this is the code that you've ever seen a million times, and here we just see there's a single stream connected. I'm not on the Wi-Fi, and we don't have a lot of extra time, actually no extra time. So, but we could serve up a lot of streams. I mean, this is how we serve the internet nowadays using Go web servers, right? So this is a great way to go about doing this. All right. So our last demo is going to be object classification /tracking. Let me make sure, oh yeah, okay, I did that. With a deep neural network and a drone. You know, as one tends to do these days. All right, so the drone is a DJI Tello. It's going to be a good time for me to bring out my drone here. Boot it up. Is it booting? Okay, yeah, it's loading. Have you rebooted the drone, ma'am? It's in flight. Well, I suggest you get some altitude before you reboot. Can I get your name, please? Click. That's customer service in about 6 months. Oh, yeah. So if I go back and I just run my hello, that way we can see it. So this is my DJI Tello drone. It's $99 US. It's the latest drone from DJI, the Chinese drone manufacturer. This is a very interesting drone because it has built into it, its controls are entirely commanded by an Intel Movidius 2 neural compute chip. So that is a chip that's used for deep neural networks and edge device machine learning and some other interesting things. So in this case, that's actually not only doing the computer vision processing on the drone that it uses, but it's also all of the flight controls. So it's pretty cool. I don't have enough hands or space. All right. So I'm going to connect to my drone's Wi-Fi, because all drones need some type of wireless connection. Make sure that my joystick is still turned on. Yes, it is. Okay, excellent. And I'm going to call up my good friend Francesc to the screen. Francesc has been my mic stand before, but he's never been my test subject, target, participant.
Victim?
Victim, I prefer, that's kind of foreshadowing. I don't think we should go there yet. All right. So let me get my command line here. Or actually, let's take a look at some code real fast. Probably should have done that first, huh? So this is going to use Caffe. Caffe is a deep neural network framework from Berkeley, UC Berkeley. It's very, very popular for deep neural network machine learning applications. Quick description, what is a deep neural network? So a neural network is any software which is designed to mimic the way that we sometimes think that the synapses of the human brain work. Again, it's not exactly the same because it's not an analog phenomenon, it's a digital representation. A deep neural network is one where the inputs are connected to hidden nodes which are connected to the outputs. It's not directly connected to the inputs and outputs. And so multiple hidden layers are what are needed for you to consider yourself true deep neural network these days. So we're going to use an OpenCV built-in face tracking SSD model Single-shot multi-box detector is a type of deep neural network which works in an interesting way, kind of similar to the Cascade Classifier in the way that it was able to reject false negatives very, very quickly. And so if it's not able to recognize any faces, it just moves on. One interesting difference between using an SSD versus the Cascade Classifier, the Cascade Classifier requires more computational resources for each face that it's able to recognize. The single-shot multi-box detector has a fixed computation that's required to process the entire field of vision. So it has a higher bar of computation required, higher number of watts that are going to be required to perform that computation, but it has a threshold beyond which you're not going to go any further, and it's able to do much more efficient processing. So we're going to use GoCV.net to do this. Running out of time. Well, the quick version is, so we're going to use the stream from the video. Camera's still on, excellent. We're going to use FFmpeg to decode that video and put it into our GoCV, and then I'm going to actually use GoBot to fly the drone. So we're going to grab each one of these frames, and then we're going to take it and we're going to place it through some code that we wrote called track face. Track face is going to take our deep neural network, or actually it's going to take our image blob, converting it into this format needed by Caffe, pass it into the deep neural network, do the inference, and then get the results back, and based on that, it will determine if we've seen a face, and if so, where it's located, and then we can navigate based on that. And then there's some different controls for my joystick. The important one is how do I take off and land? I believe that is triangle and X. Okay, cool. Good enough. Francesc, assume the position, please. Oh,
I'm happy it's a small drone.
He's a brave, brave programmer. As well as a heck of a human being. We're going to miss you, man. I just want everyone to know that I did this with love in my heart. That made it all okay. All right, so I'm going to run this code, and let's see what happens.
Nice to meet you all.
All right, so it's going to take a minute for the stream to begin. And all right, so there's our main man. So I'm going to take my joystick, and I'm going to press the launch button. I'm going to launch it. That doesn't get applause. Getting a lot of interference here. Oh, there we go. Oh. Wow, we really are. That's the worst interference I've ever seen. Let's turn on the face tracking.
I'm ready to fight it if I need to.
If you need to run, it only has about 8 minutes of battery life, so... It's looking for him. It can't find him. It's scanning each of you now. Again, you don't need to run faster than the bear, just faster than your friend. Oh, now it's coming for me. Here, boy.
It's looking at your camera, I think.
Oh. That's how you do camouflage in the near future? Wow, this is pretty bad interference, actually, I gotta say. All right, I think it's time to bring this in for a landing, so I'm gonna use the deep neural network that's running in the drone itself, luckily, for it to perform a hand landing.
There you go.
It was the Bluetooth interference. That's my story, and I'm sticking to it. All right. So hopefully you guys found that fun. GoCV.io, go check it out. So I just want to leave you with one last thought. So humanity is acquiring all the right technology for all the wrong reasons. That's what Bucky Fuller said in his seminal book, Utopia or Oblivion, The Prospects for Humanity. This book was published, I believe, in the late 1960s, and it's still just as relevant, if not more so, today in terms of his almost prescient foresight in realizing that the global economic, information, and political systems were all interconnected. And I think you can tell from the title of his book sort of the basic premise. So I want to ask you, as we take this technology, I've given you a bunch of fun toys, and all of us together have done this, but what sort of future is it that we want to use to make with them? Are we going to have a future of resource depletion where we're unable to achieve our dreams because we've simply run out? Are we going to use them as tools of control and oppression? No, we're not. Or are we going to use them as tools of liberation? So that choice ultimately is up to each of us every day when we apply our knowledge, skills, and talents. And so I will leave you with this question. What will you choose? Thank you. And I have stickers after the last talk, so thank you.
Goodbye. Thank you.